Hello, everyone, and thank you for joining our live session today. My name is Larissa. I'm an event planner at Reactor, joining you from Brazil. Before we start, I have some quick housekeeping. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience and presenters. While we absolutely encourage engagement in the chat, we ask that you please be mindful of your commentary, remain professional and on topic. The session is being recorded and will be available to view on demand here on the Reactor YouTube channel within 48 hours. Keep an eye on the chat. We'll be dropping helpful links and checking for questions to be answered by our team on the chat. I'll now turn it over to our speakers for today, so let's welcome them and thank you all for joining us.
Hello, everyone.
Hello. All right. Yes, let's go and kick it off. Thank you, everyone, for joining our first session of the series. Pamela and I are super excited to talk about all the exciting stuff going on between Azure and NVIDIA. And yeah, we won't keep you waiting. We'll just jump in. So a bit about myself. My name is Stephen McCullough. I'm an AI solutions architect with NVIDIA. And that means that I get to work with Microsoft on implementing all of the latest and greatest AI technology. And Pamela, would you like to introduce yourself?
Yeah, I'm Pamela. I'm a principal cloud advocate on the Python advocacy team. So that means I spend a lot of my time with Python developers trying to figure out how you can use Python in order to develop on top of Azure, Microsoft, VS Code, Copilot, all of those things. And of course, for the last few years, it's all been Python and generative AI and getting really deep into that.
Yeah. So a bit about this program. Microsoft and NVIDIA are working in close partnership to power the next generation of AI through deep integration between NVIDIA's accelerated computing platforms and Microsoft's global infrastructure. So this webinar series is a big part of that. We really want to show users how to best leverage the magic of Azure and NVIDIA together. So make sure to tune in as we explore these integrations and show you how to apply them in the real world. And Pamela, I'll hand it over to you.
All right. So we will put a link for the whole series in the chat so that you can sign up for all of that. It's on the Microsoft Reactor site, and everything is streamed on YouTube, and also everything is recorded. So if you missed any of them, you can catch up, but it's always more fun to catch them live too. So for today, we are going to be looking at how we can run NIM models on Azure serverless GPUs using the Container Apps platform. And we're going to be covering quite a lot, like, what are open models? What is NVIDIA NIM? What is Azure Container Apps? What are agents? How do we build agents? We're going to run some example agents using the new Microsoft Agent Framework. And then what sort of considerations do we have when productionizing? So we have a packed agenda here, but it should be fun because we're going to be covering all sorts of different technologies. So starting off, let's talk about open models. First, what does that even mean, right? There's been a lot of debate about the word open and what it actually means in the space of LLMs, right? Traditionally, when we think of open, we're thinking of open source. And that's, software where you can see every single line of code. You can use that code yourself. And there's some licensing that, says all the ways you can use it, right? But with models, it's a bit different because there's a lot that goes into a model. There's the data that goes into the model, the gigabytes or I don't know, trigabytes not a thing, but the huge amounts of data that go into training a model, right? There's the actual architecture of the model, which is how the neural networks are laid out, like how many transformers and heads, attention heads there are, like all the the internal details of the architecture of the model. And then there's the final weights that come out of the training, right? So once you get all that data, you train it on a particular architecture with a particular approach, you get out weights, which are the parameters, and usually like billions of parameters that are assigned to the neurons in that neural network, and those come out of the training process, right? So the interesting thing is that you can open up just parts of this and still be able to share models in particular ways without opening all of it, right? So when people talk about open models, they're usually talking about open weight models, which means that, somebody trained the model and then they released the weights for that model. And they also release details about the architecture so that somebody can take the weights and, use run the weights and be able to get responses from that model. But for most of these open weight models, the data is not open and the actual code that they use for training the model is not open. There are a few that are like completely and utterly open, but the majority of these models are only open weights and not open everything. And that way people can like keep, these companies can keep, some sort of competitive advantage because they're the only ones that can, retrain a new model like that, but they can still share the models in ways that other people can use them, right? Because the great thing about open weight models is that then you have a lot more ability to use them in the way you want to use them, right? Like you want to use them on your home computer. You can do that if your computer is powerful enough. You want to deploy them in a certain way on your data center hardware. You've got a lot of options there. You want to run them on your mobile phone or your Raspberry Pi or something, right? So it gives you a lot more flexibility into how you can use those models. And that's why, it's really exciting for people. I think in the future, we're probably moving toward a point where more and more of us are going to be running open weight models on our own machines. But then we'll still have the most powerful models, hosted on data center hardware, right? So it's an interesting world we're in. There's a lot of popular open weight models that you may have used: Llama, Phi, DeepSeek, Lava, Mistral, Gemma, Qwen. There's a bunch of them. We're going to be using GPT-OSS today, which is a particularly exciting model. Now, I did want to start off with just talking about how we can run open weight models locally, because that is how a lot of people are experimenting with these models. There's many different apps that you can use to make it easier to run open weight models locally. Microsoft has the Foundry local app, so that can be a really good fit, especially if you're on a Windows machine. It's designed to work really well there. LM Studio is very popular. Llama File is popular. Llama, very popular. That's the one I have because I like to have a cute little llama in my taskbar up here, and that works pretty well on my Mac. So let me do a little demo of Llama, right? So I can bring up my terminal. Let's make it way bigger. And then I can say Llama list. And you can see what I've got downloaded here. I've got GPT-OSS, Nemotron, Llama 3.1. I've got an embedding model. You can have open embedding models too. So most of these are all LLMs, the first four. So I'm going to say my Llama 3.1 latest. I'll just run that. And I will say, like, all right, make a song about running open weight models on Azure. Okay, we'll just see. I really like using the local models for creative use cases. Put another way, I don't like using them for accuracy because they are less. They have less facts in them, but generally they're very good at creativity, right? So if in case I need a song, open weight models running wild and free in the Azure cloud. That's where I want to be. We should have put, we should and with NVIDIA hardware. Like we needed a couple more NVIDIA references there. You can see it's actually running quite fast, right? V100, is that a current architecture?
No, it's probably the third or fourth generation behind the latest. The latest would be Blackwell.
Okay, so that's it. That's this is of course the issue with these models is that they're not as up to date, and so they can make references that are outdated, right? That's a classic issue with LLMs. But you could modify them to say A100 or a different one. Okay, great. So here I'm running that one. Now, as I was saying, today we wanted to really focus on the GPT-OSS models. They were released recently by OpenAI, and they're larger than the standard open weight models. So the smallest side is 20B, which means 20 billion parameters for the neural network. And then the larger side is 120B, which is really large. So some people are able to run 20B locally, but very few people can run the 120B locally. Now, these models are really interesting because they are reasoning models and they will actually show their reasoning tokens. So that's quite nice because it gives you a little bit of insight into maybe what's happening behind the scenes. They also support tool calling, which means you can potentially use them to build agents because agents are built on top of tool calling. And yeah, so I did record a video of me running GPT-OSS on my machine. I recorded it as a video because on my machine I only have 16 gigabytes of RAM, and it's not a lot to really run GPT-OSS, so it's very, very slow. It uses up all my resources, and I didn't want to destroy my computer while streaming because I want to make sure I can stay on this stream here. So it actually took, this is a 17-minute video. We're obviously not going to show it all, but it did take 15 minutes on my computer to answer the question of 2 plus 2, right? So let me get to the point where, here we go. So this is me saying 2 plus 2. And then it starts thinking. Let me show you how slow this goes in. I was sitting there actually counting to myself. This was also late at night. So I was like lulling myself to sleep with this because it takes about, this is like the amount of time it took. So it took about 12 seconds for each token to come in there. So I would sit there and go, okay, 1, 2, 3, 4, 5, 6.
Instead of counting sheep, you're counting tokens.
I know, right? And I would have totally fallen asleep doing it, except that I really wanted to, get to the end of it, right? And particularly painful to watch the reasoning because I'm like, oh gosh, how long is it gonna? Because it was like over analyzing my request, right? Okay, so finally, you can see all the reasoning, right? Because it was trying to decide whether I wanted something fancier, like whether it was a trick question, right? They're like, oh, maybe okay, let's just produce a short answer, and I was like, oh yes, right? And then it got to the end, right? So this is showing you how, it really, with open weight models, it really depends on the model and your machine and even the architecture of the model. Like this model was actually particularly designed to work well with NVIDIA cards, I believe, with the quantization it uses. But I'm on a Mac. I don't have the NVIDIA card here, right? So you can see it actually didn't use much of my GPU up here just because it wasn't optimized for that. And it just tried to do a lot with my RAM, right? So yeah, your mileage will vary with local models. I know folks who have, NVIDIA cards or have higher amounts of RAM on their Macs that can run GPT-OSS, right? But generally, this is the case with local models, with these open weight models, is that you have to figure out what is actually reasonable for you to use on your machine that you can practically use if you're hoping to use local models for things like maybe you're doing some really private personal things on your machine, or you're like offline on an airplane. When I'm on an airplane, I use these models, right? So, you just have to figure out what's a good fit for you. Now, fortunately, we can take those GPT-OSS models and we can deploy them on NVIDIA architecture in the cloud where they will work very well. So let's go over to Stephen to talk about how we're going to do that.
Yeah, thank you, Pamela. All right. So yeah, what we just saw is deploying LLMs locally. But whenever we think about how we want to deploy AI models, that are enterprise ready, it's a very different approach. And deploying an enterprise ready, scalable, high performance AI model is really not an easy task. There's a lot that goes into it. You have inference engines and monitoring and health checks and quantization and API management and so on. There's a lot that goes into this deployment. So NVIDIA solved this complexity by creating NVIDIA Inference Microservices, or NIM for short. If you've heard us saying NIM so far, this is what we're talking about. So a NIM takes all of the microservices that you need to run AI at scale, and it encapsulates them into a single Docker image. So this makes it very easy to run and very easy to deploy on a number of platforms. You can run it locally. If you have NVIDIA GPUs, you can run it in an on-prem data center. You can run it in the cloud. You can run it on Kubernetes. It really gives you all of the portability benefits of Docker and all of the high performance tuning that NVIDIA puts into these images. So whenever we talk about a NIM, we're not really just referring to the underlying model itself, but rather this entire package that goes into it. So in this package, of course, we have the model itself. We also have the different inference engines that this model might use. So in this slide, it shows TensorRT LLM, but also NIMs support VLLM and SGLang in some NIMs. So this differs between NIM to NIM, but whenever you're using a NIM, you might see that it has multiple inference engines available, and you can even select which ones that you want to use. Otherwise, it will go through a optimization process to choose the best inference engine according to the hardware that you're using and some other specs about your system. So, what are the major benefits of using NVIDIA NIM? Well, the first is that it's tuned for performance according to the model's domain. So usually when we think of AI models, we're probably thinking of LLMs, right? Like ChatGPT or Llama or Nemotron, just to name a few. But really, NIM supports over 100 different AI models that fall into all different categories. So you, of course, have NIM for LLMs, NIM for VLMs, which is the vision language model. You also have a NIM for world models like Omniverse, and also even for protein folding models. So really, NIM is a very vast world of LLM optimization. And you can think of NIM, to put it shortly, as a Docker container that has everything you need to run an optimized AI model at scale. So just to show how easy it really is to deploy a NIM, really this Docker command is exactly all that you would need. And I want to point out a few things here that are a bit important. So whenever you deploy your NIM, typically you might give it access to all of your GPUs to run on, but you can also just select, one or two of your GPUs if you want the NIM to just be deployed on specific hardware. Also, whenever you deploy the NIM, it will need access to what's called NVIDIA. It'll need access to NGC, and it will use the API key that you create for NGC and use that to pull the model weights into the container whenever it starts up. So also on top of that, you'll want to expose port 8000 to the host so that any API requests coming into port 8000 would be forwarded to the AI model, and you would receive the response from that port as well. Now in this example, I'm using the GPT-OSS 20B model and the latest edition of that. And if you go to NGC, you could browse through all of our different NIMs, each of which is its own specific Docker container. And you can find whatever model, you could find hundreds of different models on NGC, and just pull them down using a Docker run with that tag specified. So like I mentioned, all of the amazing features that are baked into NIM really help it become an enterprise-ready deployment that you can run on a variety of platforms. So specifically when we're thinking about Azure, right, what does that mean? Well, on Azure, we have the N-series VMs, which are going to have, let's say, A100 GPUs, H100 GPUs that are high-performance GPUs capable of running very large models. You can also deploy on Azure Machine Learning, AML, Azure AI Foundry, or what we're seeing today, Azure Container Apps, and also Azure Kubernetes Service. So there's a ton of different ways that you can use these NIMs and deploy them and consume them. And it's just a very flexible platform overall. So speaking of the platforms for deploying NIMs, I'm going to hand it back to Pamela, and she's going to walk us through Azure Container Apps and why that's such a great platform for deploying and hosting NIMs.
All right. Yeah, so I'll talk about Azure Container Apps. It's actually my favorite platform deploying anything on Azure. It's what I use when I'm deploying my Python applications, my full stack applications. It's just a really good fit for lots of things. And because it now has GPUs, it's a great fit for this as well. So what is Container Apps? It is a way that you can deploy containers. So you can use container standards like Dockerfile, right? And you can, define your container using a Dockerfile. You can test that your container works locally, and then you can deploy that same Dockerfile into Container Apps, and then Container Apps can, actually serve that Dockerfile at scale. And what's really nice about it is that you can actually scale from zero. So if you're doing something just as an experiment, a prototype, whatever, you can actually say like, hey, if there's absolutely no traffic going to my app, just scale down to zero, right? On the other hand, you can say, hey, I'm getting ready for launch, there's going to be a lot of scale. Let's allow a huge amount of scaling, right? And you're only going to pay for what you actually use, right? So all the compute is based off what you actually use. So for me, it's also a good fit because if I'm, a lot of times I'm just doing experiments, prototypes. So I really want that pay-as-you-go, compute-based pricing that I can get from Container Apps. Another way to think about Container Apps is being an easier version of Kubernetes. So I still haven't learned Kubernetes. It's been on my to-do list for several years now. But, basically with Container Apps, I think of it as an easier version of Kubernetes where I can get multiple containers that are communicating with each other. But I don't actually have to worry so much about the management because all of this, scaling and coordination is managed from Container Apps. So I really like it. Now, it does help to understand some of the terminology that is used when you're setting up Container Apps. So first, you have a Container Apps environment, and that actually creates a virtual network around potentially multiple container apps within your environment, because it's very often, if you're using a microservice architecture, you might have, one microservice on one container app and one microservice on another container app. And naturally, you want those to be within the same virtual network, right? So your Container Apps environment is a virtual network boundary that includes all of your container apps. And then for each container app, they can each have multiple revisions, right? Because you imagine you're doing a new deployment, that's going to be a new revision. You can, scale up and down traffic based off of the health checks of the new revision. If it's looking good, you transfer all the traffic over to the new revision. And then within a revision, you can have a certain number of replicas, right? This has to do with the scaling I was talking about, right? So that could be 0 replicas if you're not getting any traffic and you told it to scale down to 0. You could set the minimum number of replicas, make sure there's always at least one replica around. And then you can scale up to any number of replicas based off of scaling rules. So that's really powerful. And then each of those replicas is running your Docker container, right? So that's the overall architecture of Container Apps on Azure. Now, what's cool is that Container Apps now support the ability to use GPUs, right? Traditionally, you wouldn't be running these things on GPUs if you're just doing a standard backend app or microservice. But if you're trying to run something like NIM, you definitely want to be running on a powerful GPU. So this is called the GPU workload profiles when you're looking at it in the documentation. So the nice thing about using Container Apps serverless GPUs is that you get this scalability, but you also have the compute-based pricing, right? So, if you're not sure how much you're going to use, you could just pay, based off of how much you end up using, right? And then we get all the other benefits that we already talked about for container apps, right? And when we're running for the architecture we're going to use today, and this is also the architecture I generally use, right? We're going to set up a Container Apps environment. We're going to have a container app. That container app is going to pull the container from a container registry. and that container is defined with a Docker file. So whenever I'm putting together a container app application, this is generally the architecture that I set up so that everything is contained within Azure. Now, if your container is stored on another registry, like on the NVIDIA registry, then you actually, you can skip pulling from the registry and just pull directly from the other registry as well, right? So there's different ways that you can set up that. All right, so now let's see how Stephen actually deploys GPT-OSS NIM to container apps.
Let's do it. All right, so whenever we are deploying onto Azure Container Apps, there's a set of things that we need to complete first, a set of prerequisites. So the first is to register with NGC, NVIDIA GPU Cloud, and create an API key. This is going to be required for your NIM, so just make sure you have that all set up before you go ahead and proceed. Next thing you need to do is ensure that you have GPU quota for Azure in a supported region. So a couple of things to unpack there. Not every region in Azure supports serverless GPUs, and I have the ones shown here that do support serverless GPUs. So for example, West US 3, and the rest of these 5 all support serverless GPUs within Azure Container Apps. And within that, some regions don't support all GPU types, but most do. So for example, West US doesn't support the NVIDIA T4, but it supports the NVIDIA A100. And I'll go into the differences between those GPUs on the next slide. But for now, make sure that you're selecting one of these regions that has support for serverless GPUs. The third is to create your Azure Container Registry. So Pamela talked about this a bit previously, but you need the container registry to actually store the NIM Docker image that is going to be deployed onto container apps. So you could think of the container registry as pretty much an intermediate registry between NVIDIA NGC and Azure Container Apps. And whenever we're thinking about the GPUs that we want to run the NIM, there are 2 options available in Azure Container Apps. The first is the NVIDIA T4, and the second is the NVIDIA A100. So I outlined the major differences here. You can see that the A100 has significantly more memory, which is going to help run larger, faster models. The A100 is also based off of a later architecture, so it has improvements of all the developments that happened since the release of the Turing architecture. And the NVIDIA A100 is more so meant for training larger workloads, larger models, and also inference with larger models as well. The real benefit of the T4 is that it is very cost effective, especially for inference workloads and for mainstream AI applications. The A100 has very high performance, and it's meant for demanding workloads that really need that high computational power. And the extended memory, like I mentioned, helps you run larger models at higher performance. So as you're deploying and getting ready to deploy your NIM onto container apps, put some time into thinking about which GPU that you plan to use. I'll say one of the most important factors to consider when selecting the GPU is the amount of memory associated with the GPU. So Pamela mentioned at the beginning that we have the 20 billion parameter GPT-OSS and the 120 billion parameter model. And that parameter is those 20 billion or 120 billion parameters take up lots of space. So depending on the size of your model, that's going to determine which GPU you should select to run. So once you have your GPU selected and you have everything ready to go, really the process is quite simple. You pull the NIM from NGC, you tag it and push it to your Azure Container Registry, and then you deploy your container app. And it's quite simple. Azure and NVIDIA together make it very simple to deploy these models. And just to show you, what it actually looks like to run these commands and get your Azure environment up and running, I have it all outlined here. So in our first step where we want to pull our NIM from NGC, those are these commands that log in to NVIDIA Container Registry, log into Azure Container Registry, and then pull the latest GPT-OSS 20B image from NGC. Now, once we have that image downloaded locally, and by the way, you don't need an NVIDIA GPU just to download the image, but you will need one just to run the image. And so once you have it downloaded, you tag it and essentially prepare it for deployment to Azure Container Registry, and then you push it. It's pretty simple. And once you complete these steps, you should be able to go into Azure and into your container registry. Mine is just called ACA Webinar Repo. And you'll see that you have a repository for your model and with the latest tag for that model. So once you run those steps, you'll already be far ahead. You'll have that image ready to go. So next step is actually using the model. So we need to deploy a container app to actually run this model. So as part of Azure container apps, there are a couple different major components. The first is the environment. So we create the environment here. We add the GPU workload profile to our environment here as well. And this essentially is going to specify that we want to have a consumption-based, or we think of it as serverless, right? Consumption-based A100 GPU profile associated with our Azure Container Apps environment. And this is really what's going to let us use A100s at a serverless configuration. And if it throws an error here that this profile isn't available in that region, that likely means you selected a region that doesn't support serverless GPUs. So make sure you go back and check that list of supported regions. Now, once you create your environment, you run this command to deploy your actual Azure container app. And from beginning to end, this would take about 15 minutes, which is very quick for just going from 0 to 1 for running an AI model. That's pretty amazing. But for the purposes of this presentation, I just want to show you the commands so you have an idea of what it looks like. So we create the environment here. We make sure that we pass in the NGC API key as an environment variable. And we also want to have a minimum replica of 1. This will make sure that, even if we have 0 traffic, our container app isn't going to scale down to 0. Now, scaling to 0 is, of course, very, very helpful. And it's a huge part of what makes Azure Container Apps so nice for running these models. Because if you're getting 0 traffic, well, then, you don't have to run any containers and you save a lot of cost. But I imagine, if you're running just this to test it out, you probably want at least 1 replica of this NIM that you can run and test with and deploy. So once you have this up and running, you can go back to Azure and you can see in your container apps that you have, I just called my GPT-OSS NIM. You'll see under your revisions and replicas that you have an active revision running. So it'll show you the details here, and it'll also show you your endpoint URL if you go into the overview section. So I kept mine hidden for now, but I'll show you what it looks like whenever you interact with it. So if you want to test out your newly deployed NIM, you really just have to run a simple curl command. You run a post request, including the prompt, the model name, and of course the Azure Container Apps endpoint. And let's see, I'm asking it to run to tell me a funny joke about the solar system. So let's see what it comes up with. And I'll reduce the max tokens down to 100 so we don't have a large response. But I mean, first of all, just notice how quick that was. That's generating about 100 tokens, hosted away from my computer extremely quickly. So what we see is that it includes all of its reasoning tokens as well. So if we, see if it comes up with a funny joke, the user wants a revised version of the joke where the Earth is not mentioned. The assistant should comply. The user is not requesting disallowed content, so no problem. It essentially gives its entire chain of thought as its reasoning model. So, whenever I limit it down to just, a small number of tokens, that's going to be included in the reasoning tokens. So if I bump this up to, let's say, 1,000, it will take a bit longer to create all of the 1,000 tokens. And we should see a much larger response that's, completely thought out from the model. So let's see. Somewhere in here, it will have the joke for us. But yes, so yeah, we'll see how it goes. But yeah, so essentially, if you want to run and test your AI model, of course, it's the curse of the live demo.
It's fine without the jokes going there. So
yeah, there you
go. You're using like the old school API here, right? You're using V1/completion. So that's like sentence completions, right?
Exactly. Yes. Yeah. So this is using sort of the older version of the API, whereas nowadays we typically want to run the responses endpoint. So it's probably a reason that it, is outputting, so much of the tokens that are showing, different thought processes going on. Mm-hmm. All right. So yeah, now we have our model up and running, hosted in Azure Container Apps. And now we can think about, how we can really use this model in a ton of different ways. So, of course, we have the ability to, generate text and generate images. But nowadays, we're thinking about how we can use these models as AI agents. So whenever we want to use a model as an agent, we need to think about first, what exactly an agent is and what it can do for us. So whenever we're running an AI agent with NIM, we could think about first, exactly how the agent works and what NIM is doing in the background. So this diagram sort of shows an idea of how exactly agents work and what they're capable of. Lots of exciting stuff to unpack here. So it starts off in the top left whenever a user submits a prompt. Let's say we want it to, generate a fun agenda for today because we're visiting, let's say, Washington, D.C. So the agent will receive the prompt, it will plan and reason, and it will think about all of the different things that one might want to do in DC. But of course, it might need some more information about Washington, DC. It might need some information about the weather that day. It might need some information about events, let's say concerts or special events that are happening around Washington, DC that it might want to plan for. So it can use tools to go and gather that information, whether from the web or elsewhere. Now, about this tool use, this is really what kind of opens the door for what agents can do because not only can tools, request and pull in information, but tools can also be used by the agent to, let's say, output information. So if I wanted to create a tool that, let's say, made a post on LinkedIn, right? I could just give that tool to the agent with a lot of trust, and it would, create that post for me. I could say, create a post announcing, this new webinar series that we're doing. And it would create that, run code to post that to LinkedIn, and it would take care of it all by itself. So whenever this tool is executed, that information from the tool goes back into the model. And we have this kind of like critique phase where the model will examine the results from these tools and formulate a final response showing the kind of the whole picture. So for example, if we're going to Washington, D.C., it would receive information about the events and then use that to formulate its final response to the user. Now, I was playing around with an agent the other day, and you really have lots of control over the tools that are accessible to the agent. So I created one tool where it said, it was like a temperature tool. You're getting the temperature for, whatever city you're in for the day. And I hard coded it to always return 20,000 degrees Celsius just to see what would happen. And so it used the tool. It got 20,000 degrees Celsius in Austin, Texas. But sometimes it does feel like that. And so it received that number back. And in the critique phase, it said, your tool said that it's 20,000 degrees today. You might want to re-examine how your tool is working. There might be something wrong with it. So the agents are really, really intelligent, and they can even figure out when something is wrong with your tool. So they're not just taking all these responses at face value. They're really, reasoning about the responses from these tools and using them appropriately. So not only can these tools be used to, gather information or post out information, but you can also use these tools and these agents as a sort of network of agents to accomplish a particular task. So for example, if we want, let's say, a agentic workflow to write code, right? We would first pass our prompt to an orchestration agent, which could plan and interact across multiple different agents, which all have their own different tools and own different prompts and capabilities to accomplish a certain task. So this is really where the world of agents kind of expands, and you can do just an almost innumerable amount of things with agents. So lots of exciting stuff there. And Pamela is going to show us how we can use our current deployment as an agent. So I'll hand it back to you.
All right. Going back over to my screen now. All right. So what I have is actually a repo I'll share in the chat here that has all these examples. And so I've set up the .env with our container apps endpoint. And so here, what I'm doing is I'm going to show you how we can use Python packages in order to interact with the endpoint and then build up to being able to have agents, multi-agents, and agentic workflows, right? So the first step here is I'm just showing the basic OpenAI Python package, right? So, we're pointing at the endpoint. In this case, we actually don't have any particular key in front of it. We'll talk about later how you might want to add keys, but we can pass in anything for the key by default. And here I'm using what you tried to do earlier, tell a joke about the solar system, right? But I am using the responses API, right? So when you're using these LLMs, there's generally 3 different ways of interacting. There is basic completions, which is like complete a sentence. There's chat completions, like complete a conversation. And then there's responses, which is basically a new version of chat completions that's a little more optimized for tools. So OpenAI recommends using the responses API whenever you're using the GPT-OSS model. So that's what I'm going to use for all of these examples here. All right, so what I can do is let me just run this code here so we can get a joke. All right, why did the planet go to therapy? Because it had serious orbital issues and felt like it was in a gravitational crisis. Okay. All right, it was a start. Okay, so that's a basic response, right? Now, the next step is just realizing that this is a reasoning model. And so we can actually see the reasoning tokens if we want to see how the model is making its decisions, right? So here I'm giving it something a little trickier, like this question about like city planning. Okay, if the city starts offering free bike rentals, how would this impact commute? And I can set the reasoning effort. So you can set it to low, medium, or high. And then we can specifically display the reasoning tokens when we're outputting the response so that we can get some more insight into, into the actual process that went into it. So this GPT-OSS is a reasoning model. It'll always reason, but we can control the effort that it reasons at, and we can display that output. Right now, this was quite a long answer. So here we can see reasoning. Okay, so look at that reasoning. That is a one-line reasoning there. I did say low, didn't I? Reasoning, need to explain impact. Okay, let's raise it up to high and see how that changes the reasoning output here. It's probably gonna shoot past my terminal here. You can see how fast it is. Like, it was shocking for me to go from my local machine to the Azure NIM deployment because this is my first time really getting to use the GPT-OSS models with reasonable latency. Now here it is taking a little bit of time because I'm not streaming the response back. Usually, a lot of times if we're doing something user facing, we're going to stream. But here I'm just waiting for the whole response. So that means waiting for the reasoning. Okay, so all of this here is actually reasoning. So reasoning. Okay, and there. So you can see there's a huge difference between reasoning low and reasoning high, at least in terms of the number of reasoning tokens. And then there also may be a difference in the quality of the response, right? Generally, you'd assume with a higher reasoning amount, you get higher quality response. That's what they saw when they ran these models on benchmarks, like for, answering exam questions, is that they got the best results when they set reasoning effort to high. So you definitely want to keep that in mind when you're setting up these models in terms of how to improve the quality from them. There's a question, can you stream the responses? Yeah, you should be able to stream the responses from these APIs. I didn't experiment with it in this case because I usually am not streaming responses when I'm setting up agents because usually they're like kind of working in the background. But yeah, Stephen, have you tried streaming with the NIM models? I assume it should support it just fine.
Yeah, it should work just fine.
Okay. Yeah, there's a question about that in the chat. Okay, great. So then the next step is that we want to use tools, right? OpenAI, these are models that support reasoning and they support tools, right? And what does that mean, support tools? What that actually means is that we can pass in the definition of a function, right? So here, the get weather function, right? So we say, hey, agent, LLM, you've got this get weather function you can call. It takes in a location and it gives you back a temperature, right? So all we're doing is basically giving the function signature to the LLM, saying this function exists, it has this name, and it takes these arguments with these types. That is all we're sending to the LLM, right? We're not actually sending the actual function to LLM. We are just describing how the function works. And so we're saying, hey, model, you get, there's a question, what's the weather like in Paris? Here's your tools. And then when we go back through, we check to see like, okay, are they responding? Are they reasoning? Or are they trying to call a function, right? So let me run this one so we can see what it decides to do. So we can see the reasoning. It says, we need to call the get weather function with Paris, France, and we'll then provide the response. And then it says, here's the tool call. We need to call get weather with location Paris, France, right? So it says what tool we should call, but it doesn't actually call the tool itself, right? We as the developers are the ones that are actually defining those functions and calling the tools. So what we actually have to do in order to use tool calling is that we need to, define our functions, right? So here we could have the weather function, we could have a look up movies function, and then we would pass, all of that to the LLM. And then when we get back, or, you know, the recommendation from the LM about what function to call, then you actually go through and you call that function locally, you get back the response, you add it to the conversation, and then you recall the LM and say, hey, we got back the function output. Now that you see the function call output, what do you want to do with it? So there's actually a lot of code here. And you might be looking at this going like, wow, it's kind of a lot to call tools. And that's why we tend to use frameworks in order to do a lot of this for us, right? But here you can see it's got the function call detected, it's executing the function, it's doing the, actually sending it, and then, finally getting a response for, incorporates both the weather and the movie results. Ooh, there we go. So there's a lot of code here involved in calling these tools and managing the tool call results and all of that stuff, right? So that is why we typically use agent frameworks when we want to have agents that call multiple tools and handle those results and iterate, with planning and reflection and critique and all of that, right? So what we have here is a bunch of examples using the agent framework from Microsoft. This is a framework that was just released 2 weeks ago, I believe. And it's basically the successor to both semantic kernel and AutoGen, right? So they took all the best parts of semantic kernel and AutoGen, merged it into this framework, also added new things to the framework. So if you were using AutoGen or semantic kernel, you should start moving over to agent framework. And if you're not using any agent framework yet, definitely consider using this Microsoft agent framework. So with the agent framework, we can configure that to point at that NIM endpoint as well. We can define our functions here. Mine's more reasonable, rather 72 or 60. And then we just pass that to the agent, right? So this is just an example of this one is a single tool here. Right. So we see it's getting the weather, and then it says, okay, here's the weather, grab your umbrella or some boots and go outside. So that's just doing it with a single tool. But you can see our code here is really nice and clean, right? We've got our responses client, we get the weather, and that's it, right? Very nice, clean code. So it looks really similar once we add in, multiple tools. So we're just going to add in another function here. Actually 3 functions. So we're gonna have a get current date function, which is a great function to give to an agent so that agents actually know. Remember, like LLMs have no idea what time it is. So you really want to let it know. So we're gonna give it get weather, get activities, and get current date, and then say, okay, what can we do this weekend in San Francisco? And so it's going to decide which of those to call. So it's going to call first. It called get current date, which is great because that's basically, it should figure that out before it calls the other ones. And then it called the other 2, and then came back with its response, right? Then we could move up to having what we call the supervisor architecture. This is where you have one main agent, and that main agent is deferring to 2 sub agents. Right. So you can see, and the way we've implemented this is basically agents as tools. This is a common way of doing this kind of supervisor architecture where you say your tools are these, and these are actually functions that just call another agent, right? So this is one way that you can implement this, agent of agents architecture here, right? So this agent knows how to either plan meals or plan weekends. This is like a parenting helper for me because those are the main things that I do when I'm not at work is plan weekends or plan meals for my kids, right? So here it decided, which of the sub agents to use. It's going to plan the meal. That one then has its own tools that it's calling. So find recipes and check fridge. I really wish the check fridge function actually worked and like I had sensors in my fridge. And then we get back a recommendation there about the recipe. All right. And then let's look at MCP, right? We're covering everything here, and just to show you, we can do pretty much everything. So what I can do is run a basic MCP server that has some tools in it, and this has a bunch of tools for hotel booking. So that MCP server is now running, and then over here I have this code that points at the MCP server locally and says, okay, you're gonna, use these tools. Here we go. Find me a hotel for 2 nights in San Francisco. And it's going to call whatever tools from the MCP server are going to help it answer the question. All right, so there we got back some available tools. Oh, wait.
You didn't have to, and I was just saying, you didn't have to change anything about the underlying model, right? This is all just performing at sort of a layer above the NIM, correct?
Yeah, the most important thing is that you're using the responses API. That was the key thing, is to use the responses API. But as long as you're using the responses API, that's for GPT-OSS in particular, then that's it, right? It supports the tool calling and knows how to do all this stuff, right? That one actually didn't quite give the response that I wanted to give. I did make one change to these yesterday. Let me try this one. So this is another one that's using a hosted MCP server, which can look at documentation. So it has tools to look through our Microsoft Learn documentation. And so we just passed that as the tools. And so we asked this question: does Azure offer serverless GPUs? And there we go. We get back the responses. Okay. So that one worked well there. Okay. All right. So that was a whirlwind of how to build agents with reasoning models. The key here is, that with the GPT-OSS, you definitely want to use the responses API. If you were using one of the other NGC models like Llama, 3.1, Mistral, whatever, then you potentially want to play around with using the chat completions API. So basically those are your 2 options, right? And it's really easy to swap them out, right? If, you would just change this to doing OpenAI chat client, and then boom, that's going to work for the other models, right? So that's the main differences between the models is, what are they optimized for? Is it chat completions or responses? And are they reasoning models or not? There was a question, are there tools for content filtering, logging and testing? And as Carrie said, there is a bunch of logging built in to container apps. And you can, of course, also hook up the application insights. I actually did that for this one here. I said set up observability, and I actually defined my application insights connection stream in .env. So I can also see the requests come in on application insights, right? So you can use the logs on container apps for all the server level stuff. But if you also want to see open telemetry traces, then you can hook up application insights and just the way you normally would. And that will go through to your app insights, and you can do all the monitoring there. So, lots of options for how you can do logging and observability. Okay, so we have 3 minutes left. So blast through these and then see if there's any additional questions to answer. So a little bit about productionizing, right? So, here we're, set up our example prototypes to show you. But as you're going to use this in production, you have some things you want to think about, right? One of them is the private networking. So as I said, like container apps environment is a virtual network itself, but you can decide whether it's going to only allow internal traffic or public traffic. So for Stephen and I, we both set up public traffic on these so that we could, use the endpoints from our own machines and from wherever. So I can actually I can use Stephen's endpoint, he can use mine. But that is something you'd want to think very carefully about whether you want to, allow public ingress. Probably more common would be to limit container apps environment and just to the other services that are running in your environment. And so that's really easy to configure. You can also even bring your own virtual network to it. If you don't want to use the built-in one from the container apps environment, you can set up subnets, you can set up NSG rules. Just so many different options for how to set up private networking that you can customize based off of what sort of security you need. You could also think about securing that endpoint with key access. As you saw, I didn't have to pass in a key. That's the default configuration. But you could set up like a single key that you store in the container app secrets or in Azure Key Vault, and only allow requests for that key. Or if you want something that scales to a larger number of people using it with keys, where you want more control over keys, then you put Azure API management in front, and that way you get like all this key access set up. You can set up i3 throttling, you can do cores. that can be really great when you really need a lot of control over the distribution of the endpoints. And finally, scaling, right? As I was talking about, like, favorite thing about container apps is the ease of scaling, and you can, configure that all in your container apps settings. You can set up the scaling rules. You can set up the min replicas, the max replicas. You have a lot of control there. And what I suggest is set up those scaling rules and then run a load test, right? So we have an Azure load testing set up. It's very easy to set up, right? So here's Azure load testing. So you can say, like, okay, we're expecting this amount of traffic. Let's see and make sure that we can scale to that amount of traffic. So here you can see last night where my colleague Anthony was actually testing this out. And, you can simulate just a number of users, and you can see, like, okay, how are things going? How do the number of replicas increase, right? Let me refresh that one. So you can see all this data. So I definitely recommend running a load test once you've got your scaling rules set up to see if it's really scaling to what you're hoping. And there's the load test. All right. So we're now at time. If you want to try this out yourself, there's a great tutorial on the Microsoft Learn documentation about deploying NVIDIA NIM to container apps. That one is for Llama 3, but if you want to use with GPT-OSS, you just change GPT-OSS, or you can go to the NGC catalog, catalog.ngc.nvidia.com, explore, search. There we go. So you go to search, and then you can search through and see all the different models available and see which one you want to deploy to NVIDIA.
I think it would require you to sign in at first.
Oh, it must have, my cookie must have signed out. All right, there we go. Yeah. So there you go. All right. So that is what we had set up for you. And I think we did actually cover a lot of questions. Thanks to Carrie in the chat. Carrie is from the Container Apps team. So big props to Carrie for helping answer lots of questions in the chat there.
Yes, thank you, Carrie, so much. And we also have, Pamela, a couple slides forward.
Yes.
Is just some QR codes for the next episode.
Yeah, so we will also have 2 more live streams of this one. So if you have any colleagues in different time zones, you can join for the next 2 streams. So for all of the series, we're going to be doing 3 streams of every version. And the next episode after we do these ones is going to be in November about evaluating how slow your models are performing and ideas for improving model performance and benchmarking and all of that. So that should be really fun as well. All right. Well, I think we're at the end here. So thank you so much, everyone, for joining us in the chat for the live session. Thanks, Stephen, for sharing all your NVIDIA knowledge. And it was a lot of fun.
Yeah, that was a great time.
All right. Bye, everyone.
Bye, everyone. Thanks for joining.
Thank you all for joining our session today. Thank you to Stephen and Pamela for the content. We are always looking to improve our sessions and our experience. So if you have any feedback for us, we'd love to hear what you have to say. You can find the link on the screen or in the chat, and we'll see you on the next one.